Okay, good afternoon. Can we start? Okay, so firstly, any questions on projects or homework or anything like that? I think there are a couple of unanswered emails on the homework. You probably saw the extension note. I need to get back to you on your code. Mysterious problem still. But anyone with any questions? And how many of you are still on the? Okay, three. Okay, that's a more manageable count. Well, I'll state the full question. How many of you are waiting for PTEs? One, two, three, four. Okay, that's it. No one else, right? Four. Okay. Um, okay. Uh, Hang on. Patience pays off. So, um, so let's see. So today I have office hours 4:30 to 5:30. But I'm going to make it longer because I really would like you guys to start coming and talk to me about the project. So I'll stay here maybe until 8 or so, okay, after which I'll probably get hungry and we'll go home. So during that time window, come by, discuss any other project ideas. If you have your own, that's also fine. Yeah.
What room is that again?
What room?
Yeah.
6730E.
This building?
Hmm? Yeah, this building. This building, okay? Okay, so I guess 2 classes ago, when the last time I lectured, we had started down this path that we see this pattern that things which are architecturally sophisticated are very good, very efficient at doing large amount of work, but it comes at the cost that their baseline complexity is higher. So just to keep them on, so to say, ends up burning energy. So kind of when it comes when we look at platforms from perspective of power or energy, we have this tension between things which are energy efficient in the sense that joules per unit work, and things which are power low power in the sense that when they're fully running, they just consume less amount of power. So things which consume less typically also do less, and so they might be the simpler processors, 8-bit, non-pipeline, not multi-core and things like that, whereas kind of the more sophisticated processors are bigger. All those transistors just being on are going to take energy. There are also things like caches and all, which also add up to this whole thing. So in a way, when we design system, kind of ideal situation would be that they should scale in terms of their power. So if I'm not demanding, think of some time window. If I'm not demanding any work during that time window, they should consume zero energy. And if during the same time window I were to ask 10 times the work, they should consume 10 times energy. So it should be linear curve with a zero offset. So with this example I had in a smartphone kind of setting, at most of the time is basically doing nothing, and then periodically it kind of wakes up, or the user wakes it up to swipe on the screen or some system activity. Then at that time you would like to scale it. The problem that happens though is it's very hard to design systems which can scale across a large performance range. So if you just look at like processors, there are processors which are optimized for a certain band, and within that band you have ability to sort of turn a knob and do some sort of a speed versus power, or performance versus power trade-off. But there are limits to it, and a very common technique is this DVFS, or dynamic voltage frequency scaling, um, which lets you essentially, there are a couple of variants of them. One is you sort of tune the speed and the voltage is adjusted accordingly, and the power follows some sort of a quadratic or cubic curve. And the other case, which is kind of a bit more common, is that there will be recommended values of voltage and frequency, and the OS has to kind of simultaneously tweak both of them. And this is a capability pretty common now in our laptops, mobile phones, these kind of devices. Sometimes it is just to enhance the battery life, and in other cases it might even be as part of a thermal management strategy. But when it comes to thermal management, to avoid letting things heat up too much, it's usually some sort of a regulator which is sitting on the chip which handles this. So so what you see then is that for any given choice, you would have an ability to traverse some part of the space. And so I had talked about that, how one of the ways you cope with this thing then is to make your system using multiple processors or multiple radios or multiple sensors or whatever resource you're talking about, and which collectively traverse a larger part of your operating space. So you could, for example, have a big processor and a little processor. And this idea, which kind of in the academic world has been around for a fair bit of time. I mean, one of my early research projects in the space was in 2007-ish timeframes, almost 10 years ago. But made it into, these ideas made it into commercial one in, I would say, 4 or 5 years ago, when ARM introduced this thing called big.LITTLE. And now there are plenty of examples of these things, these kind of approaches on the commercial side that you see. So what is common, what happens in these things is that these are instances of a processor with the different implementations of the same instruction set architecture. So they'll all be, let's say, the ARM instruction set or i86 instruction set, but these processors would differ in their power performance points. So again, these might be things like how many support scalar units they have, so that number of instructions they can execute in parallel, how much cache they have, whether they have floating point or whether they're emulating the floating point, those kind of differences that come into play. And in this case, essentially, as far as the software is concerned, the processors are homogeneous. But so when you transfer work from one to another, it involves some transfer of state, but not much more. And then more drastically is the possibility that you may have processors which speak an entirely different instruction set architecture, have a different instruction set architecture. So in this case, you might have, let's say, an ARM processor coupled with, let's say, an Atmel processor or some more TI MSP 430, something kind of entirely different ISA. And you see these kind of things also quite a bit. And usually in smartphones and all, you would see that there are microcontrollers or of a different ISA kind of embedded and doing these kind of things. So they might continually monitor the sensor data stream and all, and when it appears that there is some significant work to be done, then they wake up the main processor, which is the app processor. So this big.little is what on mobile phones is referred to as the app processor. Okay, so that would be your, for example, the main programmer visible processor where Android runs, and so that would be the one which is this big.little. And then the tiny processor, there are actually many of them in a modern smartphone. They often are called like sensor hub and things like that, but these are embedded. Sometimes they are simpler versions of ARM following a different variant of the ARM ISA and not having the usual goodies like virtual memory and things like that. And in some cases, they may be entirely different, but they are the one which kind of are vigilant and handling stuff all the time. So together, now of course, since the instruction set is different for that real tiny guy, what that means is that you cannot simply transfer some amount of data and activate the same program. Your binary is entirely different. So in most cases, systems just let them be specialized processors like these, and they are not made programmer visible. But there have been some academic work where what they do is you write an application and two versions of it, some some part of that application may have two versions compiled, one for the green guy and one for this big.LITTLE cluster, and then you can with some application assist, you can kind of move computation around even that, but that hasn't caught on commercially as well. But collectively, you can traverse these systems over a fairly wide range of performance and power consumption characteristics that you have. So what you end up seeing then is that under appropriate control of the scheduler in the operating system, you would have these different cores being activated. So when the phone is asleep, for example, it could be that real tiny thing is the only thing which is active. And our modern devices often do need to do certain computation all the time. So there is a role to have for those processors anyway, but other times it's basically moving between this big processor and little processor, and predicting workload prediction becomes an important part in this thing as well. So the intelligence is all in the scheduler of the OS. So some early realizations of this, I think 2 or 3 years ago when they first made it into our mainstream smartphones and all. So a typical combination was to combine ARM's A15 series processor with the A7 series processor. So you would see kind of the differences that occur between these. So A7 is in order execution. Anyone knows what that means when we refer to a processor?
So if you write a program, the assembly language will be written in one order and it will be executed in that same order.
And therefore the opposite is out of order. So why? What makes it possible to do out of order? Yeah. So if there's no data dependence, so you can shuffle things around, right? So what in out of order processors, then there would be some hardware logic which will look at the instructions which are further downstream. They are still in the pipeline, examines them and says, can I swap their order? This instruction that I'm executing is going to take time. Let me go ahead and do the next one, because not all instructions need to be executed in order, because they may not need the data. One instruction may not need the data from the preceding one, for example. So A7 is in order, A15 is out of order. Another distinction you would see is the pipeline depth. The higher end processors have deeper pipelines, and therefore they're able to push the clock frequencies a lot more, but that comes again at the cost of complexity. The execution units, in case of A7, there is a single queue of instructions, whereas in A15, multiple queues, okay, which exist. What you see as a result is, and this is kind of a metric which matters quite a bit if you care about throughput, which is how many instructions you can execute per clock cycle. So all this complexity kind of goes on to improve that throughput that is there. So A15 can execute 3 instructions per clock cycle, and A7 can execute allows for 2 instructions to be set, then it has 5 execution units. So in a typical scenario, then A7 will handle kind of the background stuff and all, but then when suddenly some more intensive workload, processing of some sensor data, gaming, these kind of things come into play, then an A15 core. And actually, I haven't kept track of what the latest generation Snapdragons do. But
is it possible to lose performance when you switch all the time? Because
sure, if you switch too often.
Yeah.
Okay, so part of the thing then also is to figure out that, okay, I'm running on a high-end processor, suddenly the system seems idle. Is it worthwhile for me to shut down the big processor, go to the little one, and only to be woken up back up? So a lot of, now in some settings, you may either learn or be told the pattern of workload, okay? If it's told, it's the easy case. I mean, there are certainly some periodic tasks and all. Unfortunately, though, it's hard to offer those kind of programming APIs. So learning is the next best thing you can do, and at least academic papers have done, and I know talking with people at Qualcomm and these kind of things, these guys actually have now, at least internally, begun to apply things like reinforcement learning and all these kind of techniques where you are essentially learning the characteristics of the adversary or the user, which is what is the usage characteristic of this particular application. And once, if you can exploit it, then you can tailor your wake-up strategy to that. So absolutely. Uh, these things get into nitty-gritties, and I think currently, from what I understand, a lot of practices, these are complicated state machines hand-tuned by someone who knows things and the workload characteristic, and sometimes they're even designed for beating the benchmarks, because there are benchmarks for studying power characteristics and all, and sometimes they get it wrong also. Some of you might recollect that the previous generation of Qualcomm chips had gotten quite a bit of rap because they were actually extremely power hungry, because their power management strategy had gone awry. Okay, so 810 was it? Okay, you former Qualcomm employee or something? You are okay. So you were the culprit. Okay, but actually they got a lot of flack over it because that chip was extremely bad, and I think, I mean, people from outside can only speculate what was happening, but you would see its temperature rising, and then it would throttle itself down, and the performance will go down rapidly. So basically, they screwed up. So these are pretty complicated things internally. And again, as you can see, some of the stuff happens in firmware or whatever in the hardware level regulators. I say hardware even though these things might themselves be little microcontrollers running some embedded firmware, but they are the ones which are managing all this power management stuff. And then there is stuff which happens at the OS level, what Google does, assuming sort of Qualcomm or Samsung or whoever the chip vendors are taken care of things. So absolutely, sort of these decisions are an important part of the story. Let's see. So, okay, so I think those were the main points. I think from my recollection, at least on the Android side of things, Samsung's Exynos was the very first chip which had introduced this. So the way it worked was that they had two A15s and two A7s. I think this is 3 years old ago that it had come out. A big challenge in these things also comes, I mean, it's not simply, the story is not simply about, oh, I have processors, I break them up and all. So you also have to worry about things like, where are the interrupts going? You have to redirect the interrupt to the place where the entity listening to it is running, right? So handling of I/O, maintaining coherence of cache so that the data has the same. A lot of the usual issues that come up in any multi-processing kind of a scenario pop up here as well. So this was Exynos octa-core chip, and fairly complex piece. You can buy embedded boards around it. Okay, so in the sense that you can buy, I think there's a company called Odroid which sells just like Raspberry Pi and all. They're gonna sell these things using the very same thing. But since what, last year or year and a half ago, you have in Raspberry Pi a quad-core processor. So kind of the kind of capabilities that you normally associate. And also there are many other things where you would see heterogeneous processor cores, namely the case that I was citing here, little ring thing. So one very common variant of this is either they'll have a microcontroller or sometimes they have DSPs to handle certain types of traffic. And I refer to sensor hub, which is the microcontroller class, or usually it's a Cortex M series processor, which handles the low-level sensory data. I know Huawei has opened it up for developers. I don't know whether Qualcomm has. I don't know. I don't think so. But DSP chips on Qualcomm phones are programmable. Again, I think 2 or 3 years ago they opened it up. It's called Hexagon DSP. So there are all these processors. In fact, by the time you take a look at a complete sort of mobile processor like Snapdragon, it probably has a dozen or dozen and a half different processors. Okay, not all of them are visible to you. Some of them are for Qualcomm internal usage. Some of them, they are not visible from Android in the sense of they don't run Android, but they are accessible by in the form of a separate API. So, and whatever is happening on the mobile phone side, in pretty short order, basically makes it into the Raspberry Pis and these kind of devices as well. So task migration is the big deal. The nice thing about A15 and A7 is that they have exactly the same same instruction set architecture, same set of registers that are visible. So in theory, at least, migration of programs is literally just copying all the state from one to the other, but it takes time. Sort of 20,000 cycles, so a few tenths of microsecond. Also, you need to migrate or redirect the interrupts. So remember all those key, whatever, sensor interrupts and stuff like that. Now instead of going to the big processor, they may need to go to the little one or vice versa. And then finally, another area of performance hit is that your cache, which is tied to the processor, is now no longer valid because you're starting from a fresh empty cache, and all of that takes performance. So it's not simply the migration time, but all this other ancillary stuff which needs to be taken care of.
So this migration time is for the tightly coupled.
This is for what's it, the Exynos chip. Yeah. So for a tightly coupled case. So it's still significant. I mean, this is nothing to be sneezed at. But on the other hand, this is roughly in the same order as. In fact, this is faster than when you change voltage frequency. Voltage frequency change over times and all would probably be, depending upon your board and all, can be higher. Okay, so anytime you are changing state from one processor to another, or you are playing these games of voltage frequency, voltage scaling in particular, so deep down, this is a pretty common story there, right? I mean, I'll not walk through the thing, but basically, you have to save state, you have to move the state, you have to reactivate the state. Um, Doing if the to make it transparent to the application, you do it at a low level so that the application doesn't have to cooperate in any shape or form. If the application could cooperate, then the application could give you hints about what is the relevant state, and then you let the application reconstruct when, if and when needed. So there have also been approaches where application can explicitly declare this is the state set that matters, set of variables that matter to that application, and then the OS can exploit it. But these kind of systems are usually designed to be totally transparent. The system can just do anything under the hood, and you never kind of realize what's happening. Yeah. Pardon me? Oh, okay. So the idea behind snooping is the following: that let's say I have two caches, okay, one for the big processor, one for the little processor, and big processor is the one active, and I want to minimize the loss of performance I would have if I were to migrate to the other processor, because its cache would normally be empty. So what snooping caches do is, even while the processor is asleep, we'll keep its cache valid by snooping on the bus transactions which were going to the active cache, and then making a copy there, so that as soon as I migrate, my cache is kind of good to go. Okay, so we kind of snoop at the bus traffic in that case as part of the policy.
So the processor isn't doing anything, but the bus line is still up.
So this at the bus level. So processor is asleep, but the cache is what we do. So it's a very common practice also in multiprocessors in general, so that you can maintain coherence of cache. That is, same variable has the same value at years, of course. So let's see. Yeah. So I think those were. I don't know. Some of you might be taking Professor Yuval Tamir's architecture class. I mean, that goes a lot more into these kind of issues and all. But okay. What are the strategies as to when do you decide to migrate and all? So that in itself is a topic where loads of engineers at these companies spend a lot of time at. Loosely speaking, there is some notion of, hey, I need to do a lot more work now. I expect this was an interesting sample coming up, and maybe I could wake up the big processor, or the load is creeping up to it. So various kind of strategies are used. A very common one is that you say history is predictive of the future, at least on short time scales. So over some time window, you kind of look at what the load average was on the processor with a lot of workloads where I may have some more information about it, or they have some periodicity and all. So you can kind of exploit that as well. If the application can give you hint, that also helps.
Is there a cooperative version of this where you rely on either the operating system or the programmer, even the application programmer, to say like, I'm about to do a computer task, give me the big processor?
So academics have explored all these kind of things, and there's always this long history of this thing that who has the right piece of information to make an intelligent decision about it. Is it the application? Is it the compiler? Is it the operating system? The reality is that most application developers are either lazy or just do not know what information to provide. Okay, so while in theory application cooperation sounds very nice, it's usually a source of problem. I'll give you an example of something even more trivial. In Android, and it's probably a good case study of Android versus iOS making two very different choices. When it came to power management, when it came to deciding when to shut things down or not shut things down. So in case of iOS, the approach has always been that will not ask the application for anything. OS will decide, and admittedly, the first generation of these things were probably pretty crude, but the application, no cooperation needed. And on Android side, they had introduced the notion of locks. So an application can basically tell the operating system, I'm going to use this thing, don't lock it. Don't, sorry, I'm putting a lock on it, don't shut it down. Okay? So these are called wake locks. Guess what? They became a big problem because applications would put a lock on a resource and then forget to unlock. And so that thing just stayed up. So sort of these kind of wake lock bugs and all became an issue. And then of course strategies developed detecting applications which are misbehaving and then overriding and all. So just generally from a philosophical perspective, I think generally speaking, it's not a good idea to assume that your applications are written correctly or smartly. Having said that, if you could ensure those two big ifs, then certainly applications have valuable pieces of information that can help you. If, of course, if the whole system is a zero problem, obviously. So I think nowadays a term which has emerged which I kind of like quite a bit. It's called learning enabled systems, and I think this is an example of where by by observing the behavior of the application over time, you can learn what its workload characteristics are, and then synthesize a policy just for that. Okay, I think that's the right way to go. We have all the hooks there, and again, from discussions with sort of because it seems like, I mean, at least I know Qualcomm is doing these kind of things. I'm pretty sure Apple does too. So I think bring to bear kind of policies which learn from the data that you are observing. Okay, let's see. Yeah. So these the actual scheduling decision is also further complicated by the fact that the hardware usually offers constraints on what can migrate to what. Okay, so it's not as if I can that I have 8 processors and I can use any or all of them. So, for example, in the original Exynos chip, there were 8 processors, 4 little, 4 big. You can use only 4 at a time, and the way it worked was that there was a pair of little big, and from each pair you can select one combination. Okay, so so there were constraints on how you could use it, but then there were other ways you can organize the software as well. You can think of it as a more fluid processor kind of thing to one where maybe all 4 have to be little or all 4 have to be big with a pairwise model that I was describing. So this gets into sort of the savings, gets into the specific design that that exists. one thing to bear in mind is that the whole big.LITTLE architectural um, part really caters to the CPU power, and while you would see reasonably big gains there, they don't necessarily mean that your system power gains would be anything close to that, because the system is a lot more than just the CPU. You see memory, radio, all that kind of stuff which also comes into play. And this slide kind of shows that CPU gains may look impressive, but the overall system gains are a lot more down to earth. And it took a while for schedulers which effectively exploited these kind of capabilities to emerge in our usual operating systems. Um, I think at this stage there are reasonable things out there. In case of Linux, there's a concept of power governors. So these are kind of modules within the OS, which is where the policy resides as to when to shut down a CPU or when not to. In other arenas like Windows and all, there are well-defined interfaces, something called ACPI, Advanced something Power Interface, which is how the OS interacts with the hardware's capability. So all these kind of things kind of exist. This is Snapdragon of a few years ago. Main thing I just wanted to highlight was that these things, these embedded processors and mobile processors are essentially kind of heterogeneous multicore processors in a way. So you have these so-called app processors, which are sort of the big.LITTLE nowadays mostly, but this is what you think of the processor for running where your application runs. But then you have all these other little processors, as I was saying. So you would see in this case there are three DSPs. A couple of them are tied to the radio, so you can't really program them at the application level, but one could potentially hack into them. There's GPU, there is DSP where they run the audio codecs and all. And nowadays, there are a bunch of other things also, like iPhones, they have this motion processor, which is where some of the sensor data goes, and they run some of the machine learning algorithms to do things like step counting and all. Okay, so there are a whole bunch of other things that one other thing which I've heard repeatedly in with these people, that the big source of power consumption in these mobile SoCs is actually not so much the processor but the memory. That the amount of on the RAM on chip actually ends up sucking a lot of power as well. Apple's SoCs. So now I think we are at A10. So this slide is 3 years old. They have also been pretty much on the same path. So GPUs are being used extremely extensively now, because not only are they for graphics, but they are also used to accelerate the signal processing that you need for machine learning, which is, again, for a variety of reasons, is a very integral part of a lot of system functionality. So I think in the latest devices which came out a month or so ago, the Apple has switched to its own GPU. They previously used to use from some British company. So there's a lot of action happening there. There's also something called neural processor or something like that that Apple calls has emerged. Qualcomm has something similar. Again, these are accelerators for neural network type processing, just because it is very much a part of these modern devices. I haven't seen analogous things yet on sort of plain embedded boards, but it's probably just a matter of time. Intel does sell a USB stick, or has been handing out a USB stick with a neural network processor. So for things like cameras and these kind of applications, you would probably see these things sort of make their way into um, single board computers that we are used to. GPUs do exist on things like Raspberry Pi and also in um, uh, you could make use of these additional processors there. Some of the TI chips for embedded space have DSPs in them, so that's another possibility. In fact, there are a whole bunch of embedded boards out there which have a ARM processor or multiple ARM processors and a DSP to go with that. TI's OMAP was another contender in this chip space. They kind of died in the sense that now you don't find them on mobile phones, but some of the early generation mobile phones until 3 or 4 years ago, they were there. In fact, Kindle used to have the first few years of Kindle was all based around OMAP. I don't know what they use now. Um, what you would see in this case is um, so there are a bunch of A15s there. So there's a couple of Cortex A15s. There's a graphic thing. There is a C64 DSP. So they have a DSP sitting there. There's a video accelerator. So there's a whole bunch of stuff. And then there are also a couple of microcontroller class things, Cortex M4s. And so really a lot of different heterogeneous processors residing and all visible for you to exploit, but they're sort of loosely coupled. So there's no state migration or anything like that. Now, having said that, again, some of the academic work has tried to um, present a nicer, cleaner view to the applications, even for things like these. So they take care of hiding the different ISA from you. You write an application, and then some function can be seamlessly migrated from, let's say, Cortex A15 to the DSP, and as and when the need arises. So that brings me to one of the academic work of this nature 3 years ago, but it was a best paper winner at this conference S+, which is architecture support uh, for programming language and operating systems. So it's kind of the main prestigious conference at the intersection of um, computer architecture meets programming language and OS. And this paper out of Rice basically presented this pretty cool work where uh, Cortex A9, which is kind of a regular high-end Linux type processor, and Cortex M3, which is really a microcontroller with no virtual memory, nothing, but they provided a way where to the application developer, a lot of the complexities were hidden. And they would take care of things like when most of the time the microcontroller would be active and kind of breaking things up on the bit side, or vice versa. So kind of all the coordination and all which not instead of burdening the application developer from it, they would provide nice abstractions to do it, and OS would kind of just take care of activating, deactivating the right core, even though the cores are substantively different in this case. Okay, so much on the processor side. Next thing I want to go over a little bit was uh, that these things need to communicate with the outside world. And very broadly, there are two kinds of communications we talk about in these systems. One is communicating with peripherals of different types, and the other is communicating over the wider network to potentially other devices or data centers, and you kind of name it. Um, Oftentimes, uh, these capabilities may be off-board, but what makes a microcontroller typically, why we call it a microcontroller, is that it's not just a CPU, but it has a rich collection of these interfaces present. And when you look at these microcontrollers, a few things are very commonly found. CAN. Anyone know what CAN is? Huh? Control area network. It's a bus which is very common in American automobiles. Okay, it's kind of it's been around for maybe I don't know 30 years or so. If you look at most cars now, other except if you have an electric vehicle, you'll see this port called OBD2 port. Anyone ever okay, a couple of okay. There's a port which usually exists kind of on the behind the steering wheel, so to say. So you put your hand out, they will see kind of a white line that is with a whole bunch of pins, and you can buy these little devices for 20 bucks on Amazon, plug them in. They nowadays are on Bluetooth. They talk to a smartphone. They kind of extract all sort of data from the car, and you can also do some limited amount of control of the car, like reset those check engine light and stuff like that. In fact, when you take your car for service, what really happens is they plug a fancy machine into that port. That port is essentially the portal into the network within the car. So that's CAN bus. It's slow, very should have been obsoleted long ago, but automobile industry does move slowly. So lots of microcontrollers have it. The reason is these microcontrollers are also used in the so-called ECUs. ECU stands for engine control unit. But these are nothing but little microcontroller boards, probably a few tenths of them reside in your car. Everything in your car is controlled by these ECUs. Despite the name engine control unit, they're actually used all over. They might be your brake system and things like that. So there's a very simple priority-based protocol using which CAN bus works, and a lot of microcontroller provide support for it. I2C is used very commonly as well. A lot of sensors come in I2C, and in fact, I2C is also usually present on your PC motherboards because some of the things like temperature sensors and things like that, which monitor the health of your system, you speak I2C. It's a daisy chainable bus, so kind of multiple masters. SPI is perhaps the simplest of the bus. It's basically 3 lines, and it's used for as a serial bus as an invariant. All of these are serial. UART, all familiar with, and USB again. And there is variants of USB, USB Go, and all which kind of are friendly towards embedded devices as well. Nothing majorly new has happened in many years on this side. This is not exactly an area of lot of innovations. One thing that I would basically say out here is that in many applications, you do need to communicate in adverse settings, lots of noise, electrical noise and all, potentially over long distances and in hundreds of meters. So what you do see is that buses which are designed for those often use differential voltages, so as opposed to ground and a signaling thing, so that they're more robust, higher speed. They may use shielded cables so that they're more immune to noise. So those kind of things happen, and many of these things over time have also evolved. So like CAN bus used to be pretty slow, but now there are megabit per second type versions of it, and so on and so forth. In some cases, things are beginning to change. For example, in cars, they are switching to a gigabit Ethernet type thing. And some cars already are. I mean, Tesla, for example, is all some version of Ethernet. So CAN bus has been obsoleted in many cases. Also, a lot of European cars use something called time-triggered protocols. It's a different kind of a bus standard. A lot of European car manufacturers internally. But because American law requires OBD2 so that has been there. Airplanes, sort of avionics, they again use other things, and nowadays you also have entertainment systems and things like that on their stuff, so a lot of movement towards Ethernet there.
Does PCIe fall under this category?
I didn't put it out there, PCI, because PCI is more of a backplane bus. Okay, so you do find PCIe, PCIe, PCI, and older buses like VFE bus and of course ISA bus, the original PC bus and all. So in the embedded space, you do find them. You can buy chassis, of course, plugging them into it. But that's not what you would find typically directly supported by a processor. Okay, so there would be some sort of an off-board chip which then creates a bus. Probably the other bus which you find in processors quite a bit, but used only inside a chip, is a bus called AMBA bus. And that is a bus from ARM. And what happens is, in a lot of these systems nowadays, when you design, instead of designing a board, you're designing a chip. You put a ARM processor, it will have this AMBA bus, then you put a whole bunch of peripherals, which you can buy from third-party companies, and you create your chip around it. So on your chip itself is running this bus inside the chip, or a network on chip is the term that is used, and there are standards for those. Okay, so I sort of with them up here. They're all inside. Communication with other embedded systems, I think, in some shape and form, is speed Ethernet, and nowadays some wireless standards as well. So you have things like Wi-Fi, obviously very common, but in other segments you have things like Zigbee, Z-Wave, and all. And I guess in this category up here, I would put wireless, something like Bluetooth. So you'd see wireless penetrating quite a bit. There are microcontrollers that you can buy which come with on-chip radios. So you really don't have to do any further design. Usually these are either Bluetooth radios or Zigbee or radio, which is the other A2.15.4. So these are the common things. I think there are some chips now also where you have processor and a Wi-Fi chip, sorry, a Wi-Fi radio. So I think a lot of these combinations are certainly available as well. CAN bus, which I pointed out, I mean, pretty old bus, nearly 40 years old at this stage. The way it works is actually super simple, but as a result, it's also super slow. Basic idea is that nodes, they talk on a single sort of wire, if you may, and they have a priority based mechanism. So the idea is that every node or every message that the node is trying to send out has a priority associated with it. And prior to sending the message, there's an arbitration phase which goes on where we try to select a winner. So there's a clock, and everyone is synchronized to that clock. And what the node which wishes to send a message does is, or nodes which wish to send a message do is, that they start first transmitting the priorities bit by bit. And the multiple nodes are driving a single piece of wire, and those, most of you are E's, so you probably have seen these things like wired and wired or, but kind of the basic concept is there's a pair of wire, there's a pull-up resistor which pulls it up to some high voltage, and then when you want to transmit a 1, you don't really do anything, but when you want to transmit a 0, you actively pull down that wire to 0 volt. Okay, so what would happen in this case is that as long as everyone is sending a 1, or I might have my logic in reverse, you're kind of essentially sending nothing, and whenever you want to send a 0, you're pulling it down, and every round, those who lose, and they detect whether they have lost or not by saying what are they transmitting and what are they receiving. So if what I transmit and what I receive is the same, that means I'm still in the game. Whereas if what I transmit is different from what I receive, that means someone triumphs me. And so we go through n rounds of this thing until a winner is remaining, assumption being that no two entities would have the same priority. So at the end of n bits, we are going to have a winner, and now I have the bus, and I'll go ahead and transmit things. As you might imagine, all of this stuff, plus the fact that you may have the scan bus running all over the car and all, so there are delays, and therefore the speeds are pretty slow, 250 kilobit per second, which is really painfully slow. A few megabits in the more modern versions with shielded wires and stuff like that. But as you might imagine now, the kind of things we are trying to do in our cars with lots of sensors and stuff like that, this hardly carries over. So, I mean, if you look at high-end vehicles now, you have a few radars and a few cameras, and needless to say, all sort of other goodies for comfort and all. So there are higher speed networks at this stage which are there. One of the concerns has been that they add a lot of weight, and they also introduce failure points. So the new standards which have begun to come out are essentially Ethernet kind of stuff, gigabit Ethernet, but on a single twisted pair or something running, so that you keep the wiring costs low, get high speeds, be still robust to the high temperature and otherwise pretty brutal environment that exists in a car. So, so evolution certainly have been happening when it comes to these buses, but nowhere near the same pace as what you see on the processor side. I think the bigger story has been wireless, that is movement away from wire to wireless. So a bunch of standards and things out there. So on the short range side, you have IEEE 802.15.4, which is a family of standards, and they are being used quite a bit in sort of building automation and these kind of things. But smart lighting and smart meters are perhaps a big playground for them. There is Z-Wave, which actually comes from a private company, but they managed to get to the market early on. So while their protocols and everything are patented, but you can buy their chip and then create products. So a lot of the products you find at places like Home Depot and all are using Z-Wave. Bluetooth, we hear obviously a lot about. Lots of interesting innovations happening there as well. And the subset of it, big.LITTLE, which is meant for very low-rate devices, which competes head-on with some proprietary protocol called AND, which actually you still find quite a bit in heart rate monitors and all, but gradually the big.LITTLE low-energy version of Bluetooth is sort of taken over. Wireless HART is used more in the industrial space. Is for real-time communication. One of the nice things with HART and wireless HART is they make you guarantees about latency that the packet will see in going from one to another. Wi-Fi is kind of the mainstay in longer range kind of thing. In really wide area stuff, there are a bunch of other things which exist, but there are other protocols also. So I mentioned earlier on DSRC, which is for cars. It's essentially based around 8.11. It's used for cars to talk to each other, and it's used for cars to talk to um, traffic lights or sensors on the roadside and things like that. So that's an example of something based around this. There is also for metropolitan areas where again they use of these things. So a bunch of I think what makes I guess all these connection standards interesting is that there are always going to be a bunch of them because firstly there's a distance issue, short range versus long range. There's a rate issue, which is those which are designed for really sporadic, let's say 1 hertz or slower type communication versus the radios which are designed for tens of megabit per second type communication. And they're just the deal. Cellular radios also play an important role. Interestingly, one of the issues which keeps cellular radio penetration uh, not as wide as it otherwise could be is the whole issue of how do you provision a connection. So typical devices need a SIM card. SIM card means you need a separate account. It needs to be managed. Uh, they charge for it. Okay, so now if you're trying to deploy a large scale system where you may have thousands of devices, you the only way currently is to have thousands of these devices provisioned by the companies like AT&T and all, and that becomes a big hindrance, at least for the end consumer. Um, and of course, as we begin to see devices with cellular capability coming into play, the actual market model is still playing out. So, like the new Apple Watch, for example, which has a cellular connection, um, it can only work as an adjunct to your main cellular connection, and you have to pay $10 a month. On the other hand, we are also used to wireless devices where sort of the details are hidden from you. So if you buy a car with telematics capability, you don't go around paying AT&T or T-Mobile or Verizon connection for that car. It just comes bundled with the car. Kindle has always been like that. So there is these providers which are called M2M or machine-to-machine service providers. And what they do is they essentially take care of all this aggregation. So they work with AT&Ts and the likes, but to manufacturers or to consumers, they basically provide kind of you have a bunch of devices and you don't need to individually provision them, and they kind of take care of those details from you. You can buy a cellular board even for your embed, for example. Now, okay, so these are usually sold by these kind of companies, and then they become your data service providers, and they aggregate across a whole bunch of devices, and they essentially take care of all the nitty-gritties of having a separate data connection. I mentioned, I think in one of the earlier slides, also there's something called LTE Direct, which again Qualcomm has been pushing for a bit, and that is for your phone or devices with cellular radios to talk to each other, and so probably in coming years we will see that. 5G, I'm sure you may have at least heard about it in news media as to how it is coming and all, and there are some other rollouts happening as we speak. One of the things that uh, cell companies and standard bodies are sort of advertising about 5G is that it is being optimized for use in IoT applications, and they mean a variety of things around it. But one of the things that they are highlighting about it is latency. So currently with cell phones and all, the latency in the sense of the way the radio link works, the way the access protocols work and all, you are talking about latencies which can be in hundreds of milliseconds. And that's quite problematic. So guarantee that they are aiming for in 5G is sub 1 millisecond latencies as seen by device to base station. Okay, of course, then you go over the internet and all, and there might be additional stuff. So 5G would probably be another technology which, if things sort of turn out the way they're advertising, I mean, might bring devices there. So between LTE Direct and 5G, you might begin to see sort of more routine sensors might directly be connected to the cellular radio as opposed to going through the Z waves and Zigbees and all. Okay, so time will tell. I think a lot of them is always going to be about economics, which is even if technically it may be feasible, if I have to pay $10 a month for every motion sensor in my home, that's not going to work. So I think the pricing structures and all are going to play out also over time. Let's see. Some other relevant standards to know about in this case. Um, so there's something called IPv6 low PAN, low power wireless personal area network. So IETF, which is the body which maintains internet related standards, some years ago introduced IPv6, which is the version of internet protocol designed with much larger address space and a whole bunch of other goodies, with the anticipation that we are going to have a large number of devices on the internet, and that's indeed the case. Although penetration of IPv6 has been much slower than what they anticipated for a variety of reasons, but the main thing is that 6LoWPAN is the version of IPv6 designed specifically for low rate, short range, resource constrained wireless links, essentially meant for embedded devices. So the problem was that in going from IPv4, which we currently use, to IPv6, the address size went up from 32-bit to 128-bit. So all the things happened were in the direction of actually requiring more bandwidth and more resources. So then 6LoWPAN emerged to start doing things like header compression to reduce message size. So for example, what 6LoWPAN does is, if I have a wireless link and I have IP packets going one after another on it, if you look at the header is huge. Okay, in fact, it's bigger than the packet size of a lot of those underlying radio standards. But if you also sort of ponder over it, you would see that the content of the header doesn't change much. It's succeeding packets on the same link. So what they begin to do is, firstly, only send things which are changing, so kind of make it like a connection, and then compress it. So those are the kind of tricks they play to bring down the message size. Uh, we want to play this 6LoWPAN is what runs on top of the 802.15.4, which is the lower level radio standards, to provide essentially IP to your light bulb. Okay, so all these new products which have emerged in recent times, where these sensors and various kind of appliance modules and whatnot in your home are using a connected internet, they're kind of working with this. Um, there are a whole bunch of other things which have happened in this space, not necessarily with equal success, but at least 6LoWPAN seems to have gathered other traction. And then finally, Bluetooth, lots of changes and evolution happening there. And again, Bluetooth also belongs to a standard standard of IEEE standard, IEEE family standards, of which Bluetooth is one instance. Some other things which have happened is the way the radio technology has also evolved in this context. So, and new capabilities which are being gained. So, for example, a lot of these radio standards, including Wi-Fi, have begun to now gain capabilities such as not only do they let you communicate, but also discover your location. So, Wi-Fi, which I think is currently being approved, would have the capability to support your radio knowing its location. So there are a lot of useful information that you don't do. So there are constant kind of advances which are happening on that front as well. Okay, so let's do the following. Let's take, I'm at a transition point, so let's take a 5-minute break and then we continue again.
Sorry, to book an appointment to go to your office, like 4:20, or is like first come first served?
Yeah, maybe I know there's a website which have a queuing system. I mean,
Yeah, because I suppose that today probably is going to be one of the
is your
days
day.
yeah.
Yeah. I'll, okay. Probably won't happen for today, but yeah, I think for future I'll adopt a queuing system.
Thank you.
I mean, the programming model is to available for both needs. Yeah, the GPU replaces any concept. But what you will see is chips where GPU and CPU are together using all radio. So you can, in theory, some of these they do let you program, okay, but remains rather not very common. So usually you will need some microcontroller as your host, and then you will hook up your module, where the module also has a processor, but that processor is taking care of some of the programmability. So like you can find these different modules where besides the radio, they may have some sensors. You can kind of program it by sending certain commands. Sample with over 10 every 1 second. Yeah, so Okay, let's shall we start? Actually, I want to take a short break to uh, just find out everyone's name and all because now that the class size has kind of become a little bit uh, more sane. So maybe what we can do is starting from this end, just go by your name and something interesting about yourself. I guess. I mean, I'm just my attempt to do some name to face correlation, but it could many of you would be looking for project partners and all, so it might be useful. So,
My name is Shobhan.
Shob,
Shobhan.
Shobin.
So, so I come from India, and so I graduated in 2016. I worked in a company called Dexter Industries.
What industries?
Dexter Industries.
Dexter Industries, okay.
So, for 1 year as application and support engineer.
Okay.
Yeah,
Yeah.
that's pretty much.
Cool.
And I'm from China. I graduated from UW, University of Washington, Seattle, just this year. And this is my first year in the graduate school. I'm currently focusing on circuits and embedded system. I'm actually looking forward to look more into FPGA applications and design and stuff like that. This is where I
Have you,
want to start.
d-
Yeah.
d- have you also worked in the industry or
Nope.
no? Okay.
Yeah, I've got some one interns in Siemens China, but not
Okay.
really.
Okay. Cool.
Yeah.
I'm Shreya and I'm from Bangalore, India. I worked in Synopsys for a year. I was in VBA development,
Mhm.
and right now, and my hobbies are painting and music.
Cool.
I'm Aman. I come from India too. I graduated in 2014. I was working in Qualcomm for last 3 years.
In Bangalore.
Yeah, Qualcomm Bangalore. I
Mhm.
was in systems simulation validation team.
Okay.
I'm Vishrat. I'm from India too. I did 1 year internship at Symantec, and I'm more into like security and forensics.
Symantec here or back in India?
Symantec in Toronto. I did
In
my
Toronto.
undergrad
Okay.
Jay, I'm from Irvine, and I was a competitive swimmer for a while.
At UC, you did your undergrad at UC Irvine or?
I wasn't. No, I went to University of Arizona. And
Okay.
they're like the best of the best. They're like Olympic level. So I was like,
So-
I was one level below that, so I couldn't swim.
So you participated in nationals or?
I never made it to nationals. I guess 2 levels.
Okay.
I was like
Okay,
D2.
still
like
many
like a
levels
D2
ahead of
school.
me. So.
Not D1.
Okay.
I was like a D2, but I went to a D1. So
Okay. Cool.
I just went for fun.
My name is Leon. I'm from Macedonia, but I lived in Austin, Texas for 12 years where I did my undergrad at the UT Austin. And I focus on embedded systems and image processing. My name is Ahmed. I'm from Egypt. I graduated from Maryland, and I came straight here. Embedded systems.
Okay. Can you speak loud? Okay.
My name is Isha. I'm from China too. I graduated here this March. Currently, my focus is search and
I think being in circuits and embedded system is actually not the most interesting thing about any of you. So find something else to say, because I suspect 90% of the class is in CS. Okay.
I'm Andy. I'm also Chinese. I graduated from the University of Nottingham in UK, and I plan to work in the area of robots.
In robotics. In the area of what?
Robots.
Robots. Okay, cool.
So my name is Sochen, and I graduated from the undergraduate program here at UCLA. So I continue my study at the graduate program here.
Hi guys, my name is Sita. I just graduated from UC Santa Barbara, and I was part of the Hyperloop team.
Oh, you're part of the Hyperloop team.
Yeah, in UC Santa Barbara. Not
In
like that.
Okay. So you're taking part in that national competition, or?
I didn't go because
Okay.
the competition got delayed until August, so we left.
Cool. Okay.
My name is Sulay. This is also my second year. I'm a master's student, and I have some experience. I did an internship about image sensor, also CS maybe.
Hi, I'm Pedro. I'm from Spain. Before coming here, I was working for Airbus in the electronics control department. This is my second year here.
Hi, I'm Tamir. I went to undergrad at the University of New Hampshire. I'm a second year master's, so I graduated in 2016. And my undergrad was in mechanical. I focus mostly on controls, and I'm interested in robotics and stuff like that.
Hi, I'm Tina from China, and this is my second year as a business student. So I did an internship this summer about time
my name is George. This is actually my 16th quarter here.
What did you say?
16th.
16.
It's my 16th quarter here.
Okay.
Yeah. So.
As graduate student. No.
No.
Okay. Okay.
The only thing I want to do right now is try to get out here.
Yeah, that sounds like a good plan.
I was interning at Gigama, network power company.
Okay.
Which no one knows. And that's about it. 16 quarters.
My name is Khalid. I'm a second year master's student here. Graduated from UCLA 2016, and then I was interning at ARM as a wireless software engineer for the past summer. And then I'm interested in like full stack IoT technologies ranging from IoT security to wireless communication, and then maybe other IoT applications as well.
So I didn't know ARM did wireless. So they make
Yeah,
radios?
they have the ARM just recently bought a new like two people company called Y Center
Okay.
that really get the BLE standard
Okay.
for SIG. So
Okay.
it's a new
So new suburb. Okay, cool. Can start from that corner.
My name's Gary. I have no idea. Oh, okay. I'm from here. I went to undergraduate here, and I only speak English. My name is Curtis. I graduated from Oregon State this year. I did a couple of internships at Intel and Cisco.
My name's Ben. I graduated from UCLA in December of 2016, it's not that long ago. I've done 2 digital signal processing internships, but like embedded programming more, and also produce electronic music, so like blend signal combines all those.
Oh, cool.
My name's Arjun. I graduated from here in computer science and engineering spring of 2016. Worked at a company called Raleigh Health up in the Bay Area. I did a few internships prior to that. Um, I like my MS is in computer science instead of being a CPC, but I'm like really more interested in like this kind of stuff, and I'm really interested in intelligent robotic systems.
Cool.
My name is Ron. I'm UCSB graduate 2013. I've been working at JPL for the last 4 years. My experience is in rad hard DC-DC converters, so we power like the radar instruments on other satellites. And yeah, it's my second year here, and my real passion is mountain biking.
And there are a lot of opportunities near JPL, I guess, for.
Oh yeah,
Yeah.
there's so much biking.
Yeah. Cool.
My name is Jenny. I'm a second year master. I graduated from UC Santa Barbara last year, and I was interning at Qualcomm GPU design team.
Mm-hmm.
I'm going to graduate this quarter, and after that, I'm going to work for them.
Work for. Yeah, cool.
My name is Steve. I come from China, and I got my bachelor's from UCLA last year. The bachelor's is in computer science, so computer versatile software space. My experience about embedded system and hardware primarily came from my personal interest and my internship at Apple. I did audio system reporting to different SoCs and type right drivers when I was working at Apple. At every time I do IC soldering on relevant boards, writing software for them, making my hardware.
Okay. Total geek. Okay.
Hi, I'm Joy. This is my second year in the UCLA department, and my undergrad is University of Washington in Seattle as well. So this summer I did the eBay intern in the big data group.
Mm-hmm.
So my interest is IoT and machine learning.
I'm Susan. I'm from China, and I got my bachelor's degree in technical
wrote the driver in the firmware for a company in China with my intern, and I'm now considering ranking to ARM design in AMD my name is Wai. I'm a second year graduate student here. Now, I didn't know much about IoT and embedded system before, but I'm quite interested in that, so I want to take this course to learn more about it.
My name is Yi. I'm second year electrical engineering student, and I spent my last summer primarily working with Professor Kaiser on some instructional resource development on Earphone and SPM sensor files. And I'm interested in system design and also like incorporate machine learning in IoT systems.
I'm Xu, like first year master's student. I'm had my undergraduate here, electrical engineering. I working with Professor all the time, like for mainly focus on like embedded system, graphic design, including IoT concept, like also people want like Intel Edison, Raspberry Pi, yeah, basically. And I'm also interested in like a lot of health medical devices and all that.
Okay.
I'm Luke. Second year master in UCLA, and I'm interested in circuit design and system synthesis. So it's my first time to take the embedded system class. Maybe I'm trying to keep interested.
Okay. Well, I guess I haven't scared you yet in the end of second week. So anyway, I was just counting. There are 35 of you out here. So I guess there are some more people. So I just want to do a bit of a show of hands again. How many of you needed PTs? Okay, so keep them up. 1, 2, 3, 4, 5, 6, 6. No, yeah, 6. Okay. And my count is right. There are 35 out here. So I'm going to do one more check, and if it turns out that the total size is 35, I'll give all 6 of you PTs. Okay. So I think I can. Okay, cool. So let's move on. Um, um, so next thing I wanted to talk about was kind of a boring part of many of these devices, but in a way as important as kind of the rest, and that's the power subsystem. And obviously, sort of IoT devices and more broadly embedded devices come in sort of lots of at many different points in terms of the power requirement. But if we kind of focus on what we normally think of IoT, kind of the low end type stuff and all, even there you would see a lot of diversity in the sense some of them are designed to just plug into the electrical grid. Some of them work with batteries. Some of them even have batteries which are not easily replaceable but chargeable. Very common stuff which is beginning to happen is to do power delivery in or harvesting in some shape and form. So couple of one is kind of some sort of solar or vibration based stuff, and the other one which is catching on quite a bit is wireless power delivery. And here I'm not referring to those Qi Macs where you can put your phone and it charges. Those are still kind of all basically contact things, but I'm referring to where at a distance you can transmit power to them. So there are companies that are seeking to do all of them. Common to all of these things is that at the end you have to deliver the power to the electronics in a acceptable quality form. So that usually is the job of regulators, and I think one of you talked about doing regulators a job. I forgot what it was. So when you look under the hood in terms of a power supply system, you're going to see a few different pieces present out there. So at the end of sort of this box which I'll talk about, you get some sort of a voltage which often is not nice in terms of its characteristics. It might change, not sensitive to temperature and stuff like that. So a very important part of these systems is the so-called DC-DC regulator, which takes a DC voltage of poor quality and generates a DC voltage of right power, right voltage level, and also with appropriate noise characteristics. In many applications, this may be absent, and you may have battery directly driving the electronics, but then you are taking the risk that as the battery voltage degrades, as the battery loses energy, then your circuit is being subjected to it, and at some point you might run risks of what are called as brownouts and all, which will corrupt the battery. If, on the other hand, instead of battery, you are directly coupled to some noisier source, then you are obviously doing something. So above this sits kind of the rest of the power system, which would consist of some way of acquiring energy, either by plugging it into electrical grid or having solar panel or some sort of a wireless receiver which gets the power. You might have some sort of energy storage. Battery is the most common, but there are other options as well. Capacitors being the next main one, and there are interesting sort of trade-offs out there. And then finally, there would be some sort of intelligence out here which would manage all of this. So part of the management task out here is the flow of energy, in the sense that whatever energy is being produced, am I sending it to the regulator, am I sending it to the storage? Sometimes maybe your load on the circuit side is more than what the outlet by itself may supply, in which case you will still take power from the battery or the energy storage. So there's a complicated sort of management task which is there. It may also do things like control the harvester to maximize the energy that you are able to acquire from the environment. So it may range from trivial stuff like a solar panel orienting it correctly and things like that, to one where there might be knobs in this harvester which make you operate at what is called as a maximum power transfer point, where you are seeking to maximize the amount of energy that you can take from the outside and put it in there. Some pretty interesting innovations happening in this space currently. Just the past 2-3 years, groups that, particularly at the University of Washington, I think a few of you are graduates from there, so you might have heard about this work. Battery-less sensors, battery-less cell phones, and things like that. And what these guys have been doing, pretty very, very nice, interesting work, where they basically take energy out of the radio waves which are around us, so TV stations and cell phones and cellular towers and all, and essentially they harvest energy from that and then they supply it to the rest of the circuit. Obviously, there's relatively little energy to be had, so you still need to design the rest of your system in an extremely power efficient manner. But what these groups have shown is that it's possible to have actually certain types of embedded devices which are entirely batteryless. You can imagine a sensor which is just a PC board and it's sensing and communicating, but it has no battery, no internal energy needed. So pretty cool stuff. Energy storage. Battery is the one which we normally assume, some sort of rechargeable battery, but as I mentioned, capacitors is the other one, and a lot of interesting stuff happening in both those technologies as well. So on the battery side, I guess one of the main things that is happening is that there are batteries that you can make on chip. They're called thin film batteries, and they're basically using the same kind of manufacturing that you use for the rest of semiconductor. You kind of layer the chemicals and all, and essentially have on-chip batteries. And the other one is capacitors, and pretty cool work here at UCLA in chemistry department out here. And these are graphene-based ultra capacitors, and with energy densities approaching now battery levels. So battery's advantage is that it can pack in a given volume a lot more energy than capacitors can. But if you can bridge the gap, then capacitors have some very interesting advantages, such as battery versus capacitor. Charging time. Yeah, you can very rapidly charge. In fact, some cell phones have capacitor plus battery so that you can very rapidly charge. At least some companies are trying it. It kind of got obsolete lately because Qualcomm has been pushing this rapid battery charging technology in recent years, where they kind of drive the battery at the cost of battery life into a more rapid charging domain. What else? pros and cons, battery versus capacitor. And ultimately both store charge, right?
Simpler?
Hmm?
Is the capacitor just simpler?
Safer perhaps. Batteries, particularly high energy density ones, are dealing with things like lithium ion and all, which explode. Capacitors also explode, mind you, but lithium ion and all are particularly dangerous. But nah, I think manufacturing wise, I mean, battery certainly is more complicated to manufacture and dispose when it comes to that. Huh? Leakage, yeah. So that's an important point. So which leaks more? Huh? Capacitor. Put energy and after a while it's gone, right? Batteries stay for a long time. Huh? Well, that's energy density, right? So for any amount of energy, the batteries are always smaller. Although with graphene ultra caps, that gap has been narrowed. But yeah, you're right. And there are a couple of different things out there: size, as in volume, and weight. Okay, so there are two ways you measure energy: energy per unit mass and energy per unit volume. There's actually a third metric which is also very important, or third and fourth metric, which is power per unit size or per unit mass. So energy is energy you're storing. Power is the amount of energy I can supply in a given amount of time. And in some applications, you do need to supply energy in a burst. Okay, good example, obviously, the flash in a camera, but there are plenty of other cases where I need to supply a high amount of energy, large amount of energy in the same time window than otherwise. Other examples being, I mean, a very power-hungry radio on your cell phone and things like that. So there are often you do run into power limitations as opposed to energy limitations. Okay? Other things, batteries age. Um, I'm sure you've read about like after a certain number of charge recharge cycles, batteries degrade. Okay, capacitors don't degrade. They have a lot more charge recharge cycles. Um, there are other issues, and I mean batteries require a careful maintenance of their health. If you don't, of the battery's health, if you don't take care of it, your battery can die very rapidly. It's particularly important in obviously electric vehicles and these kind of things where we're looking at battery packs which are $20,000, $30,000. So a lot of effort goes into designing them. But even at cell phone level and all, I mean, with the whole Samsung Galaxy fiasco from last year, you could see that even in these devices, management is important. I think ultimately there was no public sort of description of what quite happened, but from the articles that I read and all, the culprit was this guy, the power manager out there. These things are pretty complicated in terms of the underlying control algorithms and all that are used. So uh, energy storage plays a couple of different roles. One is an untethered system. It is a source of electrical energy, barring those examples of battery-less systems, in which case the source is something in the environment. And then the other one is storage is often needed to take care of intermittency in the energy supply. So if you're scavenging things off the radio waves or off the sun, then you do, and then if you don't want sudden failure, then you probably need some sort of a storage there. So besides batteries and besides capacitors, there are other forms of storage also. Mechanical storage is often used in certain systems, flywheels and these sort of things. But by and large, it's batteries and ultra capacitors or high density capacitors which are there. So I've listed, I think, most of the points we've already discussed. Charge, recharge cycle, aging, stuff like that. So these trade-offs are well known, and in many systems you have hybrids, so battery plus capacitor being used together. Battery technology itself is also quite rich, and when it comes to energy storage, so when it comes to storing certain amount of energy in a given volume or a given mass, at least it's relatively safe technologies. Battery is pretty much the best we have. There are these things called fuel cells, which have always been the promise of the future. I still have a cover from Scientific American from 97 or 98, which was basically saying next year we'll see cell phone with fuel cells, and we're almost 20 years from this. It hasn't happened. Fuel cells operate by having a fuel, usually high density, high amounts of hydrogen packed together, could be methane or hydrogen trapped in a graphene fabric and graphene scaffolding. There are lots of different options. Problem with is all of these things is the moment you pack a lot of energy in a small space, you are dealing with essentially an explosion, okay, or something. So, dangerous situation. So, I guess we just never have learned how to make them safe. And lithium ion pretty much what we deal with, and the improvements there have been happening in things like how many charge recharge cycles they can survive, how well we can manage, all those sort of things. So the increments in energy storage in the battery technology have been relatively slow. With graphene, the capacitor technology is certainly improving. I've listed out here a whole bunch of other things in terms of opportunities for harvesting energy. So I mentioned the UW work, solar has been around always, vibrations is another one. Making use of just our motion. I mean, if you have wearable sensors and all, as you move around, there's a lot of sort of motion-related energy that you can scavenge. The problem with most of these things is that there isn't a whole lot of power that exists out there. You need large amounts of sort of effort to produce energy. I don't know if any of you have these flashlights that they ask you to have for earthquake kind of things and all. You have to charge them quite a bit. Okay, they are not. It takes quite a bit of effort. The other things, thermal conversion, so making use of temperature gradients and converting that, so like between hot water, cold water pipe, between hot water pipe and the environment, things like that. So you can get some meaningful energy around those as well. Solar panels have improved to the extent that you can meaningfully scavenge room level light to do stuff. Okay. I think in some airport recently, I think I saw the faucets in the bathrooms actually had little solar panels on the top. Okay. Previously, I don't know if you guys have ever wondered that how are these faucets powered up? Remember the one where you put your hand and they suddenly, how do they work? Where is the energy coming from? Right? I mean, surely they don't have a power supply line running to everything, right? It's not like that. So at least on this one, I saw these things. I think previously they are kinetic energy in the sense that they have a rechargeable battery, comes with something, and then every time you use, the flow of the water charges, and that becomes something. So there are cases like these that you can see. There have been attempts also at nuclear batteries. In fact, they are used in many systems, but obviously comes with fair bit of issues, but you can get a lot of energy that way also. Batteries versus capacitor, I already mentioned most of the trade-offs. I'm going to skip those. Current battery technology, very broadly, when you think of batteries, there are rechargeable and non-rechargeable. In some applications, non-rechargeable exist out here. I've listed, they go under the name of whether they're primary batteries or secondary batteries. So when it comes to very high energy densities, if you look out here, so joules per kilogram, this battery, lithium thionyl chloride, is way out there. Okay, many times lithium ion. Okay, but it is non-rechargeable. It is can supply only tiny bit of current. But its nice thing is it can work over a huge temperature range. So you're going to find these things just around the battery and things where your devices are being subjected to extremes of temperature. So this is an interesting batteries which exist out there. And the numbers I have out here are just meant to be representative. Things keep changing, so a lot of these numbers, I mean, I have not changed the slide for at least 4 or 5 years, so I think the latest numbers obviously would have improved. One thing which comes with batteries is that you have to manage them. So that box which I showed out here, this energy supply and storage manager, these things are pretty complicated. They are entire processors with sophisticated control algorithms and all. So these are not just some simple circuits, a huge amount of software. And part of the reason is that all these things, the source of the energy, the storage of the energy, is littered with all sort of non-idealities which one has to cope with. In case of batteries, the non-idealities come from the fact that you might think of a battery as, oh, it holds a certain amount of energy. And it doesn't matter how I extract that energy, that it will give me that amount of energy, whether I draw 1 watt out of it or whether I draw 10 watt out of it. At the end of the day, it will give me the same amount of energy. It doesn't work that way. So the effective capacity of the battery is a function of how you operate it, at how much current you are drawing from that. So the left plot kind of shows that the capacity of the battery that you can effectively use is a function of the discharge rate. So if and batteries come rated at certain current level, and if you discharge at a higher rate, you will get less energy out of the battery. So it's not simply that if I'm discharging it at 2 times the rate, then my battery will last half the time. No, it will last less than half the time. And so you kind of lose out from that. The other one on the right-hand side is showing that batteries have interesting dynamics. In particular, there is this effect called relaxation, whose common manifestation that you see is your flashlight dies, you put it aside for a few hours and you use it again, and voila, it works. So the chemical system inside the battery kind of relaxes. Now these are very simplistic view of what is much very complicated phenomenon, and I guess the epitome of these things you'll encounter in bigger systems like electric cars and all, where you have gigantic battery packs which have tons and tons of smaller cells which are packed together, and now you also have to worry about, I have all these battery cells, they're sitting in parallel, and then those parallel clusters are sitting in series, one fails, starts heating up, what happens to the rest of my battery pack? So your battery pack is then littered with sensors and all, and there's very careful management of each one of those individual packs which is going on. There are sensors which not only just tell you about the temperatures in there for safety purposes and all, but also trying to let you predict what is happening to this cell, how much load should I offer to this cell relative to another cell. So there are fair, your batteries, the term which I've seen is a software defined batteries. There is a fair amount of software which goes into just managing and making sure that the health of the battery is right and that you are able to keep track of it and operate it correctly. So that's on batteries. I see that I am at 3:48. So next topic I want to start is sensing, but instead of starting it now, I'm going to start Monday. Okay, so again, remember office hours from 4:30, and I'll try to stay as long as 8 p.m. or so. But in the middle, I might step out for short bits just to caffeine with the kind of thing. So